Now we're going to do what's called rationalizing the denominator. In other words, what this means is we're going to get rid of the radical sign in the denominator. We cannot have a radical sign in the denominator of our final answer. So rationalizing the denominator means getting rid of the radical sign in the denominator. Okay? So if I have something like 5 over the square root of 11, getting rid of a radical in the denominator when the denominator is a square root is really easy. All you have to do is multiply the denominator by the exact same thing that you already have there. That's it. That's all you need to worry about. However, if you do it in the denominator, you have to do it in the numerator. Okay? So when we multiply our numerator now, because 5 times the square root of 11 are not like terms, so I can't do anything but just write them this way. And in my denominator now I have the square root of 11 squared. Square root of 11 squared. When that exponent and that index match, the base of the exponent falls out. And there's my final answer. And I no longer have a radical sign in my denominator. Now, we aren't going to be working with this, but I need you to understand. If I have, say, 2 times the cubed root of 3. Let me write that a little bit better. The cubed root of 3. If I have something in my denominator that is anything besides a square root, now I've got more work to do. Because if I just multiply my denominator by the exact same thing, now what I end up with is the cubed root of 3 times 3 is 9. What's the cubed root of 9? There is not one. So just multiplying it by the exact same thing isn't going to help me. So now let's think about what are some numbers that I know I can get an even cubed root out of. Well, 8, the even cubed root of 8 is 2. And I want to get an even cubed root so that I can get rid of that that radical sign in the denominator. Okay? But I can't multiply anything with 3 to get 8. So that doesn't work. Let's see. The next thing would be 27. The even cubed root of 27 is 3. So 3 times 3 is 9 times 3 is 27. So if I could get my denominator to be the even cubed root of 27, then I could get a 3 in the denominator. My radical sign would be gone. Well, what can I multiply with 3 to get 27? 9. But if I do that in the denominator, I have to do it in the numerator. So now what I have in my numerator is 2 times the cubed root of 9. And in my denominator, I have the cubed root of 27, 3 times 9. But the cubed root of 27 is 3. And then we're done. So I just need you to know that rationalizing the denominator isn't always just multiplying by the exact same thing. We are only going to be doing it, I think, with square roots. So then it is always just multiplying it by the same thing. But just know that when you get into other classes, if you've got a denominator that has a root other than a square root, then you're going to have to do more work. Okay, so let's go back to some more examples of rationalizing the denominator with square roots, because that's really what we're going to be doing. Okay, so what do I need to multiply the square root of 5 with? Well, because it's a square root, I'm going to multiply it by the exact same thing. If I do that in the denominator, then I do it in the numerator. Always have to do it in the numerator too. Now I've got the square root of 6 times the square root of 5, and they're both square roots, so I can multiply those. So 5 times the square root of 30 over, and the square root of 5 squared is going to be 5. And before I actually see if I can reduce the square root of 30, well, 5 is being in the numerator here, 5 is being multiplied by the square root of 30. That means I can cross cancel my 5's. So all I have now is the square root of 30, but I have to see if I can reduce it. But look at that. I've got all prime numbers here, and I need at least a pair to make a group, and I don't have any two the same. So the square root of 30 is my final answer on this guy. Let's try another one. Okay. -8 times the square root of 18. Well, what do I need to multiply in my denominator to get rid of that square root sign? Well, because it's a square root, we're going to multiply it by the exact same thing. But if I do it in the denominator, I have to do it in the numerator. So now in the numerator, I've got -8 times the square root of 18 over, and the square root of 18 squared is going to be 18. I can go ahead and see if I can cross cancel now. Well, let me see, 2 goes into each of these, so that would 2 into 8 is 4, and 2 into 18 is 9. But I still need to see if I can reduce the square root of 18. You always have to reduce everything, guys. Oh, and look at that. I've got a pair. So remember, it's -4 times the square root of 18. So when I bring that 3 out, it's going to be multiplied with the 4. And what's left underneath is a 2. And so then I have 9. So now -4 times 3 is -12 times the square root of 2 over 9. And guess what? A 3 can go into each of these. So that brings it back to -4 and 3. So my final answer, -4 times the square root of 2 over 3. I could have tried to reduce the square root of 18 first, and so then I would have gotten 3 times 4 is -12 times the square root of 2 over 18, and now I'm going to reduce. 6 can go into each of these. 6 goes into that. 6, yes, twice. How am I ending up with a different answer? Pardon me, the original was 8, so 8 times 3 is 24, and 6 goes into each of these, so 6 goes in 4 times, and 6 goes in 3 times, and you see I end up with the same answer here and here. So either way, as long as you're reducing everything at one place or another, you're good. So that's what happens when you have just one term in the denominator. But what happens if we have 2 terms in the denominator? So let's look at an example like that. So 7 over the square root of 2 plus the square root of 13. Now, what I do here is I'm going to have to multiply with the denominator whatever will make it be a difference of squares. So to make it be a difference of squares, my x term and my y term are exactly the same, but my signs are different. So if my original sign was positive, then my new sign has to be negative, vice versa. If the original was negative, then the new one has to be positive. Okay, but if I do that in the denominator, then I have to do that same thing in the numerator, multiply it with that. Okay, so again, we need to make the denominator, multiply with the denominator, whatever will make it be a difference of squares. So now in the numerator, I'm just going to distribute my 7, and so I get 7 times the square root of 2 minus 7 times the square root of 13, because I can't do anything else. Now my denominator is a difference of squares. So I take the first term, the square root of 2, and I square it. So the square root of 2 squared is 2. And then in a difference of squares, my sign is always negative. And then I take the second term, the y, and I square it. So the square root of 13 squared is 13. And now there's nothing else I can do in my numerator. So I just leave it like this. And then in my denominator, I just subtract these and I get this. And that's my final answer. Now let's just pretend for a second. Okay, this is just pretending that our final answer, and this is correct, is this 7 times the square root of 2 minus 7 times the square root of 13 over 21. Now, I have that nagging feeling that I want to cross cancel my 21s and my 7s. But remember, I cannot do that. I can only cross cancel when things are being multiplied. So now what I can do instead is factor out the 7, and then I'm left with a multiplied times the square root of 7, the quantity, the square root of 2 minus the square root of 13 over 21. And now the 7 is being multiplied with the rest, so now I can cross cancel these. 7 goes into itself once and into 21 3 times. And so my final answer here would be the square root of 2 minus the square root of 13 over 3. Okay, let's do another example. Okay, square root of 3 plus the square root of 5 over 2 minus the square root of 7. So again, I need to multiply the denominator by whatever will make it be a difference of squares. So in this case, that's going to be 2 plus the square root of 7. Well, if I do that in the denominator, I need to multiply that exact same thing in my numerator. So let's just go ahead and do that. So I'm just going to FOIL the numerator. So the square root of 3 times 2 is going to be 2 times the square root of 3. And then the square root of 3 times the square root of 7 is going to be plus the square root of 21. And then the square root of 5 times 2 is going to be 2 times the square root of 5. And then the square root of 5 times the square root of 7 is going to be the square root of 35. Now, none of these can be reduced any further, and none are the same, so I cannot combine any of them. In my denominator now, I have a difference of squares, so I take my x term, which is 2, and I square it, so 2 squared is 4. In a difference of squares, my sign is always minus. Then I take my y coordinate, which is the square root of 7, and square it, so the square root of 7 squared is 7. And so then I just write my final answer here, which is going to be 2 times the square root of 3 plus the square root of 21 plus 2 times the square root of 5 plus the square root of 35 over negative 3. Okay? And let's do one final example. 2 over the square root of k plus the square root of z. All right, so once again, I need to multiply my denominator by whatever will make it be a difference of squares. So the square root of k minus the square root of z. If I do that in my denominator, then I have to do the same thing in my numerator. And now let's just go ahead and multiply this out. And so I get 2 times the square root of k minus 2 times the square root of z. My denominator is a difference of squares, so the square square root of k squared is k minus, and a difference of squares, and the square root of z squared is z, and I'm done. There's nothing more can be done with this guy. No comment like terms or anything, so we're just finished. And that, guys, is rationalizing the denominator, getting rid of the radical sign in the denominator.